Hello and welcome to the tutorial session today. Today I'll be discussing about nuclear reactions, in specific alpha decay. So the learning goal for today's tutorial is to define, draw and describe a alpha decay happening, and then how and why alpha decay occurs. And the last portion of the lecture would be writing and balancing some nuclear reactions. Now let's look at the nucleus, which is the very most densely packed area region of an element. Uh, Inside the atom, inside the nucleus there are two forces that are acting opposite each other. The first one is called the strong nuclear force, labeled as the blue arrows, pulling all the protons together, gluing all the protons together, check inside this small tight nucleus. And then the other force that is happening to be the repulsive forces acting opposite the strong nuclear force is created when protons are brought together in a close vicinity. Two protons being similar in charge, same in charge according to the laws of attraction, would repel each other away. Now, these two forces are acting and trying to keep the nucleus stable, but not for very long. When the repulsive force is created by the number of protons, if I keep on adding the protons and making the nucleus become more and more heavier, the repulsive forces at a point in time will overcome the strong nuclear forces and break the nucleus open. So let's look at the example of uranium element with the atomic number 92 and the mass number 238. Switching the numbers according to what is written on the periodic table does not really make a difference. The smaller number is always the atomic number, which happens to be the number of protons. And then we will assume that the number of plus charges is going to be equal to the number of minus charges, and uranium has 92 electrons as well. And to calculate the number of neutrons, the number difference between the mass and the atomic number is going to give you the number of neutrons, which happens to be 146. If I subtract 92 from 238, I end up with 146. Now we can clearly see protons being 92 and neutrons being 146. This 146 being a bigger number compared to 92 is holding all the protons together, and uranium needs that. So uranium, I would say, is a neutron rich element. So a nuclear reaction, or the reaction happening inside the nucleus, splitting apart, only happens when the element is neutron rich. So uranium atom or element inside the nucleus is experiencing a lot of repulsive forces created by these 92 protons inside it. So a time will come when the nucleus is going to become very unstable and spit out some of the particles that are inside the nucleus and outside. So specifically for an alpha decay, the particles look like this. So in alpha decay, the particles are actually having two protons and two neutrons being ejected out of the nucleus of the uranium atom. So two protons and two neutrons, the weight of this alpha particle is 4, the mass is 4. There are 4 particles inside the nucleus, and the charge is +2 because they are 1, 2 plus protons. So specifically looking at the alpha particle, we will try to define how an alpha particle looks like and describe it. An alpha particle looks very similar to a helium atom. A helium atom on the periodic table also has the mass number of 4 and the atomic number of 2. So an alpha particle by definition has a mass of 4 and charge of a +2. The only difference between an alpha particle and a helium would be the only visible difference is that I do not see electrons around the alpha particle. Okay, so an alpha particle has a mass of 4 and a charge of +2, being a helium atom. So when uranium spits out this helium atom, uranium changes into something else. So we'll quickly try to find out what that element uranium changes into. So let's look at the balanced chemical reaction. So the balanced nuclear reaction, we will have uranium on the left hand side, since uranium is the reactant, and then uranium produces the alpha particle, and the particle which we are going to calculate very soon, I have labeled this as X. Now very simply, the alpha particle is the helium atom we were looking at. There you go. And we will try to find the other element. So uranium being the reactant and the two products have been formed, is going to have a nuclear reaction happening, and in a nuclear reaction, which happens to be a chemical reaction, has to obey the law of conservation of mass and matter. Everything on the left hand side of the arrow should be equal to the right hand side of the arrow, the reactants versus the products. So we will look at the specific numbers on the top and the bottom. The mass number, when uranium had 238 particles inside the nucleus and it spit out 4, okay, the number of particles left behind would be, so 4, the number I would add to 4 to get me 238 back is 234. So 234 plus a 4 gets me 238 back. So uranium splitting into helium and this element X we are going to try to find out very soon. So let's look at the second number, that is the atomic number at the bottom. So that's 92 for uranium on the left hand side and helium has a 2. And the number that I'm going to add to 2 is 90 to get me back 92. Or basically subtract 2 from 92 and I get my element which has an atomic number of 90. So this is the key number that is going to help us determine what that element X is, with an identity of 90 protons left inside after 92 protons, after 2 protons have been spit out. 90 proton is left behind in this element. So since protons are giving us the identity of the element, let's go back to the periodic table and check what element number 90 is. So element number 90 happens to be thorium on the periodic table. So I can quickly go change this element X to thorium. The chemical formula for thorium is TH. So all in all, let's look at what is happening is uranium changing into helium or spitting out helium, that's an alpha particle, and then changing into thorium in this due process. So let's look at the practice problems, but before we look at the practice problems, let me go over defining, drawing and describing an alpha particle. Definition of an alpha particle is a particle which has a mass of 4 and a charge of +2. How does it look like? It looks like a helium particle, a helium atom. And let's look at the how and the why. The how and the why is the reason the atom splits up, the nucleus of the huge element splits up, is just because the repulsive forces inside it outweighs the strong nuclear forces. Now let's look at some of the practice problems. I have curium on the left hand side. So element curium on the periodic table has a spot of 96. It has 96 protons and it has 247. As we look on the periodic table, it has a mass of 247. Undergoes a alpha reaction, alpha decay reaction. So when an alpha reaction happens, the element is going to change into helium plus another element. So the mass of the helium is 4 and the atomic number is 2. And the other element that we form is element number 94. Now let's look at the two numbers on the top versus the numbers at the bottom. The 247 is should be equal to the number on the left hand side. The mass number on the top should be equal to adding up the numbers at the right hand side. So when curium changes into helium, which has a mass of 4, it is losing its mass of 4. So if I subtract 4 from 247, I end up with 243. The element it is going to form happens to be the number difference between helium and curium. So if I subtract 2 from 96, the number at the bottom should match on the left and the right too. So if I subtract 2 from 96, I end up with 94. And looking at the periodic table with an element that is 94 is plutonium. So this is how I decide or how I determine the other product apart from the alpha particle, the other product that is going to be formed. Okay, just a small note, all chemical reactions obey the law of conservation of matter or mass. And the sum on the reactant side should be equal to the sum on the product side. Let's look at another example. Now let's look at this thorium element, and this thorium element is still large, it's still big. Its nucleus is still going to undergo alpha decay. So when an alpha decay happens, okay, on top of the arrow, if I write down the alpha symbol, I will denote that this element thorium is undergoing alpha decay. Now straight away we will put helium atom on the right hand side. because thorium, it is going to produce helium, and then the other element will work towards it. Now, so from 232, the mass of helium was 4. So if I subtract 4 from 232, I end up with 228. Now, this mass is not going, the mass number on the top is not going to help us determine what element it is. Okay, the atomic number, the number of protons at the bottom, is going to help us, the lower number is going to help us determine what element apart from helium is produced in this nuclear reaction. So if I were to look at helium, the proton number is 2, and we started off with thorium. If I subtract 2 from 90, remember the left hand side should be matching up on the right hand side. If I subtract 2 from 90, I end up with 88. Now, left hand side 90, right hand side 2 plus 88 gives me 90 back. So, it must be balanced on both the sides. If I look at element 88 on the periodic table, it happens to be radium. So this is how we determine the other particle beside helium particle that is formed when an element, a big element, undergoes a nuclear decay, an alpha decay. Now, quickly, okay, both the numbers should be equal on the left and the right. 90 is equal to 2 plus 88. Let's look at our former example. 96 is equal to 2 plus 94 on the right hand side. They must be equal, both the numbers on the top and at the bottom. Left hand side of the equation versus the right hand side, they should add up, chemically add up. There is a small trick here to finding what the other element apart from helium atom that is going to be formed when any element undergoes a alpha decay. The trick is, if you start on the periodic table, if it is alpha decay, if I start at thorium, I go back 2 steps. If I go back 2 steps, I end up at radium. Let's start at curium. Curium is element number 96. I move 2 steps back. It is element plutonium. So that's how we get element plutonium. So all in all chemical reactions have to obey the law of conservation of mass and matter. So a very huge nucleus is going to break apart just to stabilize it, to reduce the repulsive forces inside the nucleus.